Assalamualaikum. Myself Maryam Ali. Today I'm going to show you about the different type of adders. Here the main thing about my video is about the 8-bit adder subtractor and the 4-bit ALU. As in the previous video I showed about the half adders and subtractors, but those half adder and the full subtractors are just the 1-bit half adder and subtractor and the basic blocks of these adders here. So generally there are two type of adders, half adder and the full adder. This half adders contain inside 2-bit XOR which form an EV block and result as from the end, the carry from the end. The sum is from the XOR gate and the carry is from the AND gate. But furthermore, when this half adder, two half adder combines, a full adder forms. And then when full adders combine in a series, then it is called a ripple carry adder. The ripples forms in the cout of the previous adder contained is called the ripples here. So let me show you what I am saying. Here, this block contains the example of, let me show you clearly. This block here shows the half adder here. This is the sum here, this is the carry here. But when these two half adder combines, it forms a full adder. And furthermore, when this whole full adder combined into this small block here, and this is how our ripple carry adder forms. The ripple is in a sense that the carry is coming here, but for the next full adder, the carry is coming. This is the cout for this full adder, but for this full adder, it is the cin. So this is how our ripple carry adder forms here. So basically, why it is saying here the 4-bit, as for the number 4-bit, 1101 example here, this is A, and the next is 1110 is B here. So we just put the bit here like 0, 1, 2, 3. This is like the bits form. So for the first bit we count here A1 0. This combined is a carrying goes in and output is formed. Let's see here, 0 plus 1 is 1, so the sum is 1, but as so this sum goes in here and the carry out is 0, as no carry out come from this. But if for example the other thing is 1 and 1, so its addition is 1 0 in the binary number, so this form carry here, that 1 is the carry out and this carry out goes into the cin of the other. So this is how a ripple carry adder form here. Furthermore, this whole process is a time taking, so a arithmetic logic universe form in which operand A goes here and the operand B goes here. So this is integer or in whatever set we define here, like binary, integral, decimal or hexadecimal, in which status it is, so it goes in which radix it is, sorry. So this is how the result came here. We set the operation here and we get the result here. Furthermore, let me explain you the basic things of here. Now for today we are going to study about the 8-bit unassigned adder. So what is the unassigned here? Unassigned is basically as the decimal is transformed into 2, like 1 and the -1. So the -1 and for the 1, so for these both the binary number is different. For this one it is 0001, but for this thing it is 1110. So this is how these two are different. Furthermore, this is simply the I take the carry in the sum and this form. This is the thing I am saying, that here it is the ripple form is of 4-bit, but here the ripple form is of 8-bit, as I'm showing you a 8-bit unsigned adder. So this is the 8-bit unsigned adder here. So 1 2 3 4 and 1 2 3 4, 8 here. So the 8-bit 8, so 1 bit count here, then 2, then 3, so up to so on, a ripple form and a sum here goes. So this is a waveform, or you can say this is the waveform of a thing. Here, if we, these are the two numbers. If we do it personally here, like 0 0 is 0, 0 1 is 1, but for the 1 1, here it is 1 1 is 0 1. So 0 here, and the 1 goes above. And this is how the further 1 plus 1 is 0. The 1 goes here, so triple 1. Now what is a triple 1? Triple 1 is in the decimal we get that it is 3, but in the binary number we wrote it like 11 here, or we can say 1 1. So 1 goes here and the 1 goes in the top. So 1 0 0 0 is 1, and furthermore both are 0, so we get this number here. So this is how this system works here. In here, which we get these carries, this goes into the carry out of this sum out. Here it is shown that it is, this is the system here, cin data, and this is the sum out and the carry out going here. Let me show you further. This is just a carry in here, that we get carry in here, but we can also write like carry out for only carry out if we combine two numbers and the number bit increases. Like if we add some number a plus b here, as I can give you an example, like 1 and 1 both are the 1-bit numbers, but if we combine here it is like 1 and 0. So this one is here as a C out, or we can say it is a carry out, and this is the sum here. So this is how I wrote the carry out here, but we can combine it together. Like we can also do that, input carry in, and in here a plus b plus ci. In the further statement I do that too, but that is the mixture of adder and subtractor. Let me show you. This is the code, this is a Verilog code of a 8-bit unsigned adder and the subtractor. So here these A, B are the input of 8-bit 0 to 7, and this S is the selection pin here, that we have to choose addition or we have to choose the subtraction. For addition I give 0, for the subtraction I give further I will tell you in detail how I set it. So here the output is E. I generally represent this number as E. We can also say that it is out, that is adder, or it is a subtractor here. Further, O is the, this is the I, this I is the carry in I am talking here, this carry, and the O is the carry out, which I shown you here about the 1 plus 1 is 1 0, and here the 1 is the carry out. So here, as for the subtractor, we talk about the borrow in and borrow out, but here I don't get that case. So for the subtractor it is a simple thing, but for the adder I assign a m here and this. Now further let's talk about this Verilog code, how this Verilog code forms. So basically I define a register here, a register for the output and a register for the carry out statement. So a thing is formed here, but furthermore y is just a thing that a number is going or placing into the other form. For the while system, we don't even need to define here for the model. Furthermore, this is an always statement in which we wrote the input here. Like if we have to find A and B here, so I wrote A and B. As I already said that we don't need to define the while in the module. And if I further define this module, m is equal to a plus b plus ai here as the m. So I have to define this m above here as a register. But further than this RTL view, or we can say the circuit diagram of this get large, so we get 8 mux here. Sorry, 8, we got 9 mux here. So to get a small circuit, I prefer to do it above as a sign, and further I do that. This is the waveform of this. As I told you that here, this is the if statement conditions I applied here. We can do the if, or we can also do that other statement in, I further show you in the ALU thing that I got a different statement to exchange of this if statement. So in this if statement, if the selection pin, this here is represented as, this is the binary number, 1-bit binary number, and the 1-bit binary number is 0 or 1. For the 0, I am doing the addition, and for the 1, I am doing the addition, subtraction here. Let me show you by the waveform here. So for these two numbers and these two numbers, this is the input here and this is the selection pin here. So here is the selection pin. If this selection pin is 1, then I am doing the subtraction here. But if this selection pin is 0, I am doing the addition here. So this is the subtraction and this is the addition. Furthermore, the main topic of today is about the arithmetic logic units. As for the arithmetic logic units, in this I define this cases statement as I'm showing. We can also write this if statement as a cases statement if we define s as a 0 1 bit for the 2 bit, and we get 0 and 1. Further here it is logical operations that I define here. Here are the cases from 4. We define here as A, B and E and S. E is just the input as a net number here, and S is the selection pin as I said before, and this selection pin is the basic thing which is choosing the operation here, that which operation I am going to choose or which operation I am going to select for my thing. Furthermore, the thing I defined here is register. As in the above, I define register for the output. So similar here, I define the register for this begin cases. For this E, here if I show you this RTL view, then these muxes are multiplexer, we can say that, are formed here. And further, this is the, as it is a software design RTL view, so I am not going to explain this. I am just going to explain this code here and how this code working as this waveform here. So basically, let me tell you about this operation first, and then let's go about this thing. So these are the cases here. As furthermore, we know that here we get 16 cases, maximum 16 cases from 0 to 15, as I define the selection pin as 4-bit. Let me show you about its waveform, how I form this waveform here. So this here. So for this selection pin, I have to define it by the count value. So for the count value, I assigned it the binary number, as I assigned here the cases as a binary. So I define it as a binary too. We can also define this cases thing as a decimal number. So here I define it like 100. So it is 0 to 10. But here I define 11 numbers. So let me get it. 90 counts. So it is like 0 to 10. 0 to 10 total 11. So let me define a number here. We can assign it by this arbitrary value here, 1111, or we can also define it by here by their bits here. This is how this bits forms thing. So we can also define by that thing, as it is a selection pin, so we define it like 000 and 01, then 0001, and this is how this increases. So I already run this input. If I run it here, 1 second, if I define this also as a 1111 and then just run it, yes, save. Now wait for it for a second here. And this is done. So this is the compilation of it like that. If you want me to do it as this is in the binary radix, so I define it as a undecimal. So this is how this form. Let me show you how this thing works here. If I provide it a number here, 1101, it is 1101 as a 15, and this 1011 as a 13 number here. So let me get you here. Let me erase first this whole thing. Let a plus b. Addition is simple as we do before, but let me show you once again. 1101 and the other number I took is 1011. It is 15. It is 13. So this 1 is 0, 1 is 0, 1 0 1, and this triple 1 is 11. So 1100. Let me show you here. It is also showing that 1100 in the plus. The subtraction here. So in the not subtraction, I define it as a divide here. So for the divide, we are going to use this 1101 and the 1011 here. So this is how this works. We just put it here and this form a 0001 thing here. So as for this, I just put the 1011 and this get subtract. For the subtraction, we get 0, we get 0, and for the thing we get 0, and for here 0. For by subtraction we did this, so 0 1 0, that thing. So this is the addition here, but here the waveform doing it itself, so we don't have to go in the depth here. For the AND gate, 1101 1011. So as for the AND gate, we know that when both are 1 only, then it is 1, otherwise it is 0. So 111, as 0 comes, so 0 0, and this is 1 here. Let me check it for you. 1001. Further, it is the OR gate. For the OR gate, as we know here, that for the OR gate, if both are 0 only, then the statement is 0, otherwise it is 1111. Just as it is shown here, 1111. Further, it is logical OR. Logical OR shows that a statement is true or a statement is false. as both are 101 and 1111. So both are going to get an answer which is logical. For the logical OR, it is 1111, so it is whole true. So we are going to say for the true here is 1. True represent 1, false represent 0. Further here, greater or equal to. For a greater or equal to, if we see it by 15 equal to 3, and it is obviously wrong. Further, this is the case statement is not true as 15 is never equal to 3. And as double equal is showing you that the case statement is going to check its binary number, it is a binary or it is a hex or further thing. For the XNOR, we simply take the OR not and the other thing. For the concatenation, what is the concatenation here? For the concatenation here, it is like that. A, the number I took A is 1101. So for these, the bits are 0, 1, 2, and 3. Here I define the bit 20. 2 to 0, the bit are 1, 0, 1, and the further the third bit. Third bit is 3, so it is 1. So the concatenation is going to be like 1011. Let me show you down here too. And the further E condition here. Condition is the A and B. The first statement is A here, the second is B. For the 4 bit, from the 4 bit of A, I choose a 1, and from the 4 bit of B, I choose 0. So 1 is greater than 0. So is it shown? Yes, it is true. And this the further 1011 thing is. So this is how these operations form, and this is how a Verilog code of arithmetic logic units form. So this is the topic, and here hope so you understand it, and thank you.